Hello everyone, thank you for attending this presentation. My name is Anthony Ortiz and I'll be talking to you about local context normalization. It is well understood that normalization usually improves convergence on neural networks. In late 90s, Jan LeCun and his collaborators showed that having the input of a neural network ledger being normalized to have zero mean and similar covariance produce faster convergence. But most of the normalization ledgers proposed before 2015 were doing normalization locally with the purpose of encourage contrast enhancement. More recent normalization ledgers, on the other hand, apply a much more global normalization in which feature activations SI are normalized in a divisive subtractive way using mean and standard deviation calculated based on a set of features SI that tend to be entire dimensions. The normalized feature activations are then scaled by a set of learned parameters gamma and shifted by parameters beta. Batch normalization, for example, performs the normalization of its feature activations using the mean and standard deviation calculated along the entire batch dimension. And because of the use of the batch dimension, batch normalization have certain drawbacks. The more important one is related to the fact that batch normalization works great when the batch size is sufficiently large, but when the batch size is small, model strength using batch normalization tend to degrade in performance. Multiple normalization ledgers have been proposed to address this issue, including ledger, instance, and more recently group normalization. But it's important to notice that all these normalization ledgers perform a type of global normalization in the spatial dimension. This normalization along the entire spatial dimension of a feature does not encourage contrast enhancement at all, washing out important signals and degrading performance of the models. We propose local context normalization as a normalization ledger in which each feature activation is normalized based on the statistics calculated on a window around it and the filters in its group. But now, for every feature activation, a mean and a standard deviation needs to be computed, and that's expensive. But we present an efficient way to do this calculation by using the integral image trick and applying dilated convolutions with a special 2x2 kernel using dilation rate equal to the window size. To test the performance of our proposed local context normalization, we conducted a large set of experiments for the task of semantic segmentation, object detection, and instance segmentation. We tested semantic segmentation on the Cityscapes dataset, and this table is showing the performance of the different normalization ledgers for a different set of network architectures popular on this task. We can see how our proposed local context normalization outperform all other normalization ledgers. This figure is showing a qualitative comparison between the predictions obtained while using local context normalization and the ones obtained using group normalization. And we can see how the predictions using local context normalization are sharper and also are able to segment properly small objects. We also show results on the task of aerial image labeling, and we can see how local context normalization outperforms all the other normalization ledgers. This is also true for the task of object detection and instance segmentation on Microsoft Cocoa dataset, in which we are able to outperform all other normalization ledgers. In summary, local context normalization outperforms all previous normalization ledgers for the task of object recognition, semantic segmentation, and instance segmentation while keeping the benefits of not exploiting the batch dimension. The code is available on this GitHub repo, and thanks for attending.